So we actually kind of already, no, we didn't kind of, we actually already did this, we just didn't name it as such. But this ties together, so the fundamental theorem of calculus ties together differential calculus and integral calculus, right? So this is the definite integral from a to b of f of x dx is the limit as n approaches infinity of the sum of I equals 1 to n of the little rectangles, right? Where all of this happens. And we know that if f of x were a positive function, then this integral, which is equal to this limit, is also equal to the area under f of x from a to b, right? The area between the x-axis and the curve, which is equal to f of b minus f of a, where f is any antiderivative of little f. And this statement, where is true for any continuous function f, whether the function is positive or not. So if it is positive over the interval, then you're getting the area between the x-axis and under the curve, but the statement is still true. And here we go, the fundamental theorem of calculus. If f is a continuous function on a closed interval a, b, then the definite integral from a to b of f of x dx is equal to f of b minus f of a, where f is any antiderivative of little f. Big F is any antiderivative of little f. Another notation for this, and the notation we'll basically be using, is to say the integral from a to b. I'm going to run out of these things. Tomas. Oh, you've got one.
Oh, I got it. Thanks, yeah.
Oh, look at that. All right, so this notation here, so this is the antiderivative, and then we put a bar down, and we put the bound of the integration. All right, so let's do it. So example 1, evaluate and interpret its value. So we're going to start off with a reasonably easy one. We've got x cubed, negative 2 to 4. So what do? Put an equal sign there. So what's that equal to? So we need the antiderivative, right? Which is? It's been a long time. 1/4 x to the 4th, yeah, so x to the 4th over 4. Okay, and then what we're going to do is put down the line and say from negative 2 to 4. Okay, so that's a notation that we're going to use, right? You write down the antiderivative and you write down the bounds of the integration. Which is equal to, so now this can be evaluated. So it's 4 to the 4th over 4 minus negative 2 to the 4th over 4. And 4 to the 4th over 4 is 4 cubed, which will be 64. And negative 2 to the 4th is 16, divided by 4 is 4. So 64 minus 4, which is 60. This is asking for what's the interpretation of this, right? Because we know that x cubed looks like this. And we're going from negative 2 to 4. So we have a couple of areas that we're looking at, right? So if we call this A1 and call this A2, then what does the 60 represent? Area, which one though? So in terms of A1 and A2, what did you do to get that? Just the difference between them, right? A1 minus A2 is equal to 60. So the area above the x-axis minus the area below the x-axis. Okay. So if we wanted the actual area, what is the area enclosed, we would have to work these out separately. Take the absolute value, add them together, right? That's what you can do. Or take the upper function. In this case, the upper function is x cubed. In this case, the upper function is x equals 0. But easier to just take the absolute value. Negative 2 to 0, and from 0 to 4. Next up. All right, so we might want to do a little bit of simplifying. So how are we going to handle this? twice.
Miss Westbury, call the office, please. Miss Westbury.
And stuff's out of order from what I got. Oh, okay. Hang on. I know. I'm realizing that, right? It's like, yeah, you never know. It's like, some people, when they do these notebooks, put each example on a different page, and some people don't. In this case, they didn't. Okay, what are we going to do with this? As a first step. Multiply it out, yeah, expand it out, right? I mean, you're not going to do an antiderivative of that. We don't have the skills yet. Okay, what do we get? 3x squared plus 6 minus 1. Okay, so we've got 3x squared plus 5x minus 2 dx, right? That whole quantity in the dx, right? It all comes as a package. So now we want to do an antiderivative for this. Should be pretty easy, right? Should be. Should be. And since we're doing a definite integral, right, we don't need to put the plus c in. I mean, if we did, we would add it on and then subtract it off. So that's not necessary here, unlike on the test where it was necessary, yet sometimes left off for some reason.
Yay, I learned not to do that.
Oh, not like I didn't tell you don't do that before, but yeah, don't do that. And what's our bounds? So we're going from -2 to 1. Okay, so yeah. See, this is why I would have done it on a separate page. Okay, so we substitute in the upper bounds. We've got 1 cubed plus 5 halves times 1 squared minus 2 times 1 minus, and I like to keep this separated, right? And we can work this out. Simplify. So, I mean, the first one is pretty easy, right? 1 plus 5 halves minus 2. Now, how much detail do you want to see? Can we look at that and just say that's -8? We've got minus -8 is going to be plus 8. Or do you want to go minus and then work out the second bracket? And then distribute. We'll do this. Minus, so let's just go with this. So we got -8. -2 squared is 4, and the 2 goes into 4 twice, so this will be plus 10, and this will be plus 4. All right, so what do we got here? -1 plus 5 halves minus, so what do you got there? 14, and minus 8 is 6, so minus 6.
Wait, -1. Because it's 1 minus.
Oh, sorry, 1 minus 2 is -1.
Okay.
I was collecting that.
Yeah.
Minus, then this worked out to 6, so minus 6. So -7. Just keep that over here. -7 plus 5 halves, which is -14 plus 5 all over 2. So -9 halves are -4.5. So it asks for the interpretation, so what does that mean? If we get a negative value. Yeah, the area under the x-axis is larger than the area above the x-axis, right? Okay. So I mean, you could sketch this out if you wanted. It's a quadratic. It opens up. It's got zeros at 1/3 and -2. So -2, 1/3. It does something like this. So we've got the area below. And let's say there's 1. I get the area above. Let's say the area below the x-axis is greater than the area above the x-axis. And that's why we're ending up with a negative value for that. Again, if you wanted to work out the area, you would have to do these two separately, take their absolute values, and then add them together. Okay, so there's evaluating the definite integral, right, which could give us a positive, could give us a negative. What does it mean? If it's positive, the area above the x-axis is greater than the area below. If it's negative, the area below the x-axis is greater than the area above. And if for some reason we know this function is always above, is always positive, then we will just have found the area, right? Okay, so if f of x is always positive, this opened up as a quadratic up here or something, then we would have found the area underneath the curve above the x-axis between the bounds. Okay, now we're here. Okay, so what are we going to do to simplify this? Yeah, I would just divide everything out by t, right?
Like your future is so bright.
What?
All right, let's just hope for good weather next Tuesday. If the weather next Tuesday is like this Tuesday, it'll be good.
It was a little worse like that.
It was weather good last year? There's a few years where it just rained. I think last year's actually was okay. I remember it now.
It would be.
Okay, what do we got? We got t plus, what's the next term? T, so t to the negative a half minus,
Not much, but okay.
well, you can write it as 2 over t, you can write it as 2t to the negative 1. And so we want to find the antiderivative of that. So first term is t, antiderivative is? Yeah, t squared over 2, 1/2 t squared. So increase the power by 1. Second term is? So you got to increase the power by 1. It's going to make it what? T to the 1/2. Okay, so when I multiply the half, how do I get a 1 up here? Got to put 2 up front, right? Okay, so now we've got 1 t to the negative 1/2. Okay, there we go. Why? No, this is a positive a half, right? This is going to give you this, right? And t to the negative 1 or over t. What do we do there?
Log of the absolute value.
Yeah, so 2 ln t, right? Well, and 2 ln absolute value of t. Okay. Although our domain here is that t has to be greater than, well, I guess greater than, greater than 0, right? Because we got the root sign in there, and we've got a t in the denominator, so it can't be 0. So we're okay. And what are we going? 1 to 4? All right. So all we do is, yeah, work it out, right? So I like to bracket off the first set, although it doesn't really need it. I still like to, bracket 1/2, and then we'll substitute in the 4. So working out the first term, it's equal to 1/2. Okay, so I got parentheses around the first expression, just sort of sets it off and says this is at 4, right? Minus, and then this is at 1. And it's plus. That's plus. That didn't become a Okay, so we can kind of evaluate what we can evaluate. Maybe just do that here. So 4 squared is 16. Square root of 4. Okay, and I mean 4 is positive, right? So we don't need the absolute value sign there. I guess we can drop the parentheses, right? Equals, and just remember you're distributing the minus through, so it's supposed to be minus 1/2 minus 2 plus, well, what's ln 1? It's just 0, right? Okay, so plus 0. All right, so we just work this down, right? So we got 12, 10, minus a half, so it'll be 19 over 2. Minus the ln of 4 squared, so we can move that 2 up as a power, right? And give us 19 over 2 minus the ln of 16. And that's all we can do. Right.
Will we ever use the actual value of u?
No. Not without a calculator. Okay, next one. So we're going from negative pi over 8 to pi over 8 of secant squared of 2x dx. All right, so nothing special. We just need something whose derivative is secant squared. So formula sheet at the end. So tan x, tan has a derivative of secant squared. Okay, so it's going to be tan, but it's got to be the tan of 2x, right? Because we need a 2x in between, yeah. And then chain rule says we're going to have to put a half up front, right? So 1/2 tan 2x, right? So derivative of tan 2x is sec squared 2x times 2. And we've got sec squared 2x, but not a times 2 in front, so the half in front takes care of that. And our bounds. All right, so all we do is go in and substitute, starting with the upper bound. Actually, move this over. So 1/2 tan 2 times, starting with the upper half, 2 times pi over 8 minus 1/2 tan to negative pi over 8. So that's a half tan pi over 4 minus a half tan of negative pi over 4. Easy numbers. What's the tan of pi over 4? 1. What's tan of negative pi over 4? Negative 1. Yep. So we've got a half times 1 minus a half times negative 1, which is 1. Not so bad, right? Why did you not move? This one's a little more complicated. And we'll learn methods to handle this. I mean, we should be able to suss this one out, but there are methods to do this. That's what we're going to spend, the part of the next little while on. So think of this. Let's think of this. And so we get the 1 over x squared plus 9 times 6x dx. So the 1 over x squared plus 9 should tell us, well, how do I get a 1 over x squared plus 9? A ln, okay? So let's do the ln of the absolute value of x squared plus 9. Okay, so what's that going to do? If I take the derivative, what will I get?
1 over x squared plus 9 times 2x.
Times 2x. Okay, but we need, so what are we going to do?
3.
We're going to throw a 3 in, right? So if I take the derivative of this, I'm going to get the 1 over x squared plus 9. Cool, I want that, right? But I also get, by chain rule, a 2x, I want a 6x. So we'll just toss a 3 in front. Okay. And again, there are systematic ways to do this. And what are we going from? 1 to 4? Okay, so now we just substitute in. So what do we got? Right, and they're both positive, so we can drop the absolute value. So we can simplify this. Let's pull out the 3. And laws of logs. What can we do with ln 25 minus ln 10? It's 25 over 10. And 25 over 10, well, that reduces to 5 over 2. And then what can we do with the 3? Move it up as a power, right? So the power, so we use the subtraction becomes division, multiplying. So it's the ln of 125 over 8. Okay, and we can leave it like that. Okay. Good. So it's looking, it is, kind of doing the chain rule. You're sort of reversing the chain rule in a sense, right? And, again, I think that's tomorrow or the next day. 2 sine theta cos theta. How do you do this? There's actually a couple of ways, but let's start with one.
Cos x squared. 2 ln sine. Cos theta. Oh wait, no. Sine squared.
Sine.
You can, but mine's more.
Sine squared theta, is that?
Yes. Yeah.
Sine 2 theta.
Or negative.
Sine 2 theta. Okay. Let's start there. It's actually both. Or either, but okay. Well, let's do it both ways to see what happens, right? I mean, does it matter? I mean, should it matter? Shouldn't matter. Okay, so we'll say, okay, so you're going to go from negative pi over 3 to pi over 2 of sine 2 theta. Okay, so what's the integral of sine 2 theta? Jeez. So we're going to need a cos 2 theta, right? Because the derivative of cos 2 theta will be sine. Oh, sorry, it's not sine, it's minus sine 2 theta. Negative 1/2 cos 2 theta. Right, again, just check it out, right? So what's the derivative of cos 2 theta? Well, it's negative sine 2 theta. But I want it to be positive. So we're going to put a negative in front. But then the 2 is going to come out front. So it'll be negative 2, so we put the half in there. And we're going from negative pi over 3 to pi over 2. So all we do is substitute in negative 1/2 cos of 2 times pi over 2 minus negative 1/2 times the cos of 2 times negative pi over 3. Making sure all the brackets balance out there. Okay, so we got negative 1/2 cos pi minus, so this will be plus 1/2 cos negative 2 pi over 3. All right, so we just got to figure out what those values are. What's the cos of pi? Cos pi is negative 1. And the cos of negative 2 pi over 3. So that's got negative 2 pi. That's in quadrant 3, right? So it's going to be negative. It's got the same value as pi over 3, cos of pi over 3. So it's cos of pi over 3. It's like a half, right? Supposed to be negative a half then?
Yeah.
Because it's in quadrant 3, right? I mean, negative 2 pi over 3, or, I mean, what's the reference for that? It'd be like, yeah, 4 pi over 3.
Yep.
All right, what do we got? A half minus a quarter, or 1/4. Now, what was the other thing you said? Somebody said, oh, well, that could just be sine squared theta?
Yeah, couldn't just the derivative be sine squared theta?
Yeah, it is.
Oh, okay.
I did it.
So that might be a little bit easier, right? I mean, it's probably going to be easier. We don't have to do the halves and the whatever. So sine squared theta from negative pi over 3, pi over 2, so that's the sine. Should I write like sine squared pi over 2 or sine of pi over 2 all squared? It doesn't matter. Same thing. So sine squared pi over 2 minus sine squared negative pi over 3. Okay, so the sine of pi over 2 is 1.
I know you want.
1 squared is 1. Sine of negative pi over 3 is the same as positive pi over 3, except with it's negative, right? Because it's down in quadrant 4. Sine of pi over 3 is root 3 over 2, so it's negative root 3 over 2, but it's being squared, so who cares? It's 3 over 4. 1 minus 3/4. 1/4, right? So your choice. One works out a little bit easier than the other, I think, right? I mean, but they both give you the same answer, so it doesn't matter. You know, so you might want to look and just say, well, is there an alternate? You know, I've got this minus a half cos 2 theta, and take 3 or 4 seconds and say it's worth it or it isn't, right? Cost-benefit analysis. Do I want to spend more time? I don't guarantee everything, but you know, if you can recognize this, then it's sort of like, oh, that's going to be a little bit easier. Or a little bit easier. Indefinite integrals. So we use the symbol capital F of x to denote the antiderivative of, I wonder why sometimes we put a dash there and sometimes we don't. It seems capricious. In antiderivative, sometimes we just write it as all one word, and sometimes we put a dash in there. We're anti-antiderivative. I don't know. I don't know either. Do you think it's better with a dash or without?
It's
Mine.
All right.
I can't learn when there's a dash in it.
I'll get you some white. We will now use the symbol, the integral. So now we are not putting bounds on, right? So same symbol, integral, right? Due to, did anybody tell you who did that? I don't know what's up.
He better than
It was a Riemann sum, so maybe it was him. I don't know. To denote the antiderivative, I should have known that. Okay, so the antiderivative of f of x can be expressed in 2 ways, right? Capital F of x or the indefinite integral. So this is called the indefinite integral if f of x. I think that's supposed to be of f of x. Because if f of x, I don't know, sort of. I'm going to go with all right, so the indefinite integral of this, now you bring in the constant, right? So this is just the antiderivative, right? It's exactly the same as we've done for capital F of x, the general antiderivative. Okay, we don't have a bound. If it's a definite integral, it has the bounds. And you could do the plus c, but on the one here you'd have 5 cubed plus c minus 1 cubed plus c, and the c's will disappear. So a definite integral gives you a number, right? Which if the function is positive is the area under the function, and if not, it's the difference between the area above and the area below, right? And if it's negative, you know the area below was greater than the area above. If it's positive, then it's the other way. And if you want to calculate an area, as we did with antiderivatives, again, you got to split it up, right, into the absolute value of the different intervals. All right, so what is the integral of x to the n dx? So we know we got to increase the power by 1, and then that's going to come out front as a number. Okay, so you could write it as 1 over n plus 1 times, you just write it as x to the n plus 1 over n plus 1. I believe we took a maximum of 1 mark for no plus c's. Okay, the integral of 1 over x dx.
On the absolute value of x plus c.
Right. Sine kx.
Negative 1 over k cos of kx plus c.
Yeah. Right, so you start with, what do I do to get sine? Well, it's the derivative of cos, right? Oh, but then it's negative. And then the k comes out because of the chain rule, so we need negative 1 over k. So the next one,
1 over k sine.
1 over k sine of kx. And at the end, plus c. E to the kx. 1 over k. Yeah. B to the kx.
One over k kx plus 1 plus c.
Close.
Dang.
I'm gonna do this one over here.
Kx plus 1.
Sorry?
Plus.
Okay, so here, what are we trying to do? We're trying to do b to the kx dx. So we're going to say b is equal to e to the ln b. It's not capricious. I mean, the reason we're trying to get that e in there, right? Because we've just done the e. So b is equal to e to the ln b, right? I mean, it's like saying log base 5, whatever. So b to the kx is equal to this, e to the ln b to the kx, right? Just raising both sides to the kx, which means that this is equal to e to the kx ln b, right? Power to power, just multiplying the power, right? And so that's b to the kx. Okay, and that's b to the kx, right? Which means then what we're doing is the integral of this. So we can now change that to the integral of e to the kx ln b. Now, what do we know about k ln b? It's just a constant, right? Okay, k is a constant, ln b is a constant. Okay, so it's constant. It's like this k here, right? But it's k ln b. So then, what do we do with that? Well, we can, let's do that here, I guess. Pull it up, right? It's like 1 over k. So now it's 1 over k ln b. E to the kx ln b plus c. Now, we're not going to leave it like that because the thing we were originally trying to find was what's the integral of b to the kx dx, right? Well, this is the integral of b to the kx, right? So, and the e to the kx ln b is b to the kx. So this could be replaced with b to the kx, as can this. So the integral of b to the kx is equal to 1 over k ln b, b to the kx plus c.
Oh.
Okay? I think it's on, is it on your formula sheet?
Let's see it.
No?
No. Or why can't it not just be like b kx plus 1 over k? Why does that work out?
Well, because of all this.
But if you find the derivative of that, it does give you bkx.
Are you sure?
Plug some numbers into it. See if it matches.
Yeah, try it.
So does the kx.
I don't know. I'm not gonna write that.
Okay, two properties of integrals. If you are integrating a constant times a function, then what do you think happens?
I think the constant.
You can move the constant outside, right? So it's equal to the constant times the integral of f of x dx. And if you are integrating a sum, then it's probably separated out as the sum of the integrals, right?